Welcome to the Transum podcast, a monthly roundup of the new features on the transum.org website, providing mathematical puzzles, games, learning activities, and the ever-popular mathematics lesson starter of the day. Here's your host, John Tranter.
It really doesn't seem like 1 month since I recorded the last podcast, but it has been. So, welcome to podcast number 135 for February 2026. And you know what I'm going to say next. It's time for the puzzle of the month.
Percy and Nellie Codd are brother and sister from a large family. Percy was 19 pence short of the amount needed to buy a badge. Nellie, meanwhile, was just 1 penny short of affording the same type of badge. They decided to pool their money to buy 1 badge to share. But even together, they still didn't have enough. Here's what we know about the Codd siblings. Percy has 3 times as many sisters as brothers. Nellie has twice as many sisters as brothers. How much would it cost Mr. and Mrs. Codd, Nellie and Percy's parents, to buy badges for all of their children?
That's the Transum puzzle for this month. The challenge is set. Have a think. Make a plan. You have 1 month to figure it out. Send in your solution as soon as you can.
So if you get an answer, I'd love to hear how you or your students solved that puzzle. Fire off an email to podcast@transum.org. Wonderful. Looking forward to hearing from you. But while you think about that, you may have rewound the podcast and listened to it again. That's no problem, of course. But if you're still with us, let's get on with some of the key resources added to the Transum website during the last month. Wrong but close is a 5-level multiple choice activity where none of the answers are correct, but one is significantly closer than the others. So students must calculate the exact answer first using mental methods or even estimation methods, and then identify which option is nearest. So the distractors are based on common misconceptions, so students can just eliminate obviously wrong answers. Progression from basic multi-digit operations through to complex problems with powers, roots, fractions and percentages. And it makes an excellent diagnostic tool because you can see from the wrong answer that the student has chosen exactly what the misconception is. So have a look at that. The links to all the things I talk about are in the newsletter, transum.org/newsletter. Pin possibilities. Now that's a new combinatorics activity in which pupils work out how many different pin codes are possible under a range of rules and constraints. So the questions start with simple cases, such as fixed length codes with or without repeating digits, and then move on to conditions involving parity, palindromes, fixed digits and digit sums. So it works well as a quick starting activity. Level 1 is quite short, or it does pave the way for a sort of a deeper investigation of counting strategies. So have a look at that. Remember, the link is in the newsletter. Another new exercise is called decimal sequences, and as the title suggests, requires students to have 2 key skills. First, they should be confident adding, subtracting, multiplying and dividing decimals. And secondly, they'll be able to answer questions about arithmetic sequences, geometric, and a couple of other sequences thrown in for good measure. So that's called decimal sequences. Now, distance time graphs can be drawn to represent a wide variety of different situations, and you can now find an animal race. Yes, you heard it, an animal race A rabbit, a turtle, and a fox race along a course with obstacles, some of which they trip over. And basically what you have to do is figure out what the distance time graph might look like for any of the three animals individually, or what they would look like if they were all plotted on the same set of axes. Now, this section of the podcast is called John Got It Wrong, because in my last new podcast, I mistakenly gave the 2025 date for Chinese New Year instead of 2026. So the correct date is the 17th of February, 2026, and it will be the year of the horse. I mention this so that you are aware of some of the Chinese-themed activities you may like to share with your students as sort of a nod to recognizing this international cultural celebration. Shading inequalities. Now, this is going to open a can of worms, because questions sometimes ask you to shade the wanted region and sometimes ask you to shade the unwanted region. And the inequalities they provide might be describing the wanted region, or the inequalities might be describing the unwanted region. Now, students generally learn and are happy with the fact that if the boundary is included, you draw a solid line, and if the boundary is not included, you draw a dashed line. But that doesn't work if the inequality is describing the unwanted region. So, in short, the style of the line should always match the wanted region. It's a subtle difference. So here's an example. Students are asked to randomly choose two numbers and think of them as X and Y. They were then told that everyone could have Friday afternoon off unless their X was less than 3, or their Y was less than or equal to 4, or the sum of their numbers was greater than 10. So can you see those three statements describe the unwanted region? So when drawing this and plotting the lines and doing the shading, you have to remember that the style of the line represents the wanted region, the students that are going to be happily taking Friday afternoon off. Bit of a subtle difference, but it raised its head in my domain this last month, so I thought I'd mention it.
You can find Transum Mathematics at www.transum.org.
Okay, here's an interesting story. So if your students are already using coordinates confidently, could you mention to them that there are maybe different ways of doing things?
You know, there's a very specific kind of anxiety that hits you when you're wandering around New York City.
Mm-hmm.
But it's not the anxiety of being in the city itself. In the city, on the streets, everything makes sense.
Right, you're on a grid. It's logical.
It's Cartesian, yeah.
Yeah.
If the street numbers are going up, you're going north. If the avenues are counting down, you're going east. I mean, you always have to try to get lost in Manhattan.
It's arguably one of the most rational urban layouts in human history. You're essentially walking on a giant piece of graph paper.
Exactly. You always know your coordinates. It's safe.
Yeah.
But then you take a left turn. You step off Fifth Avenue and you enter Central Park.
And it all just disappears.
It vanishes. The straight lines turn into curves. The concrete is gone. It's just trees. And you realize, oh, that guy who designed this place, Frederick Law Olmsted,
Yeah.
he tricked you.
He absolutely did. That was a documented design principle of his. He called it the pastoral ideal.
The pastoral ideal.
Yeah, the whole goal was to induce a state of mild disorientation. He wanted you to get mentally lost so you could escape the city grid.
Which is poetic and beautiful and all that.
Yeah.
Right up until you're late for lunch on the Upper West Side, your phone is at 4%, and you have no idea if you're walking toward Harlem or Midtown.
That's when the pastoral ideal stops being a vacation and starts being a navigational nightmare. I mean, the park's 843 acres.
It's huge.
Getting turned around is a rite of passage.
But, and this is why we're here today, what if I told you the grid didn't actually disappear? That it just went undercover?
It went into stealth mode. It's hiding in plain sight.
Today on the Deep Dive, we are unpacking one of my absolute favorite hidden secrets of New York City. We're looking at a system that's been sitting there since 1910, just waiting for people to notice it. We're talking about the secret navigation code stamped onto the lampposts of Central Park.
This is the ultimate insider hack. And what I love about the research we have for this is that it's not just a how-to, it's really a story about user interface, about legacy infrastructure.
And how a tool for maintenance workers over a century ago has accidentally become a superpower for modern walkers.
I love that framing. Unintended utility. So here's our mission for this deep dive. We are going to turn you, the listener, from a confused tourist spinning in circles into a Central Park insider. By the end of this, you're going to be able to walk up to a random piece of metal and read it like a compass.
No phone, no map, just you and the hardware.
So let's start with the object itself, the lampposts, because I've walked past these things 1,000 times. They're iconic, you know. Cast iron, painted that Central Park green.
Those are the Henry Bacon lampposts. And Henry Bacon isn't just a random name. He's a heavyweight. He's the same architect who designed the Lincoln Memorial.
Wait, really? The Lincoln Memorial guy designed the streetlights in Central Park?
He did. He was commissioned back in 1907 to create a standardized look for the park's lighting. So you're looking at a piece of architectural history, but the part we care about isn't the aesthetics, it's the data.
Right, because if you actually look at the post at the base, usually you see numbers. Usually 4 digits. Sometimes they're embossed right into the iron, sometimes on a little metal plate.
And to me, that just looks like bureaucratic noise. Inventory item 4452. You just assume it's a serial number.
Which is exactly what it's supposed to look like. It is utilitarian data, but it's not a serial number. It's a geocode. It's a coordinate system.
Okay, so let's crack this code. Let's say I'm standing there and I look at a post. The number is 7401. What are those first 2 digits telling me?
The first half is your anchor. The first 2 digits, in this case 74, they correspond directly to the nearest numbered cross street in the Manhattan grid.
So 74 just literally means 74th Street.
It is that simple. You are standing on the invisible geographic alignment of 74th Street.
Wow. That's deceptively simple, but it's so powerful.
Yeah.
Because it just pierces the illusion of the park. It tells you, hey, don't be fooled by the trees. You're actually parallel to 74th.
Exactly. It cuts right through Olmsted's design. The lamps are there whispering your latitude to you. It anchors you vertically.
So that handles the up and down. 62 means I'm south. 96 means I'm way up north. But what happens when you get past 99th Street?
Right, so this is where the system has to adapt a little. Obviously, a 2-digit code breaks. So once you go north of 99th Street, the street indicator becomes the first 3 digits of the code.
So the code expands.
It does. You might see a sequence like 10204. In that case, you just take the first 3. 102, you're at 102nd Street.
Okay, that makes sense. But the thing is, knowing the street is only half the battle.
Right.
Knowing your latitude is great, but it doesn't tell you if you're on the east side or the west side. And that's usually the bigger problem.
Oh, absolutely. That's the horizontal problem. And that is what the last 2 digits of the code are for. They give you orientation and depth.
Orientation and depth. I like that. So let's go back to our example. 7404. We know 74th Street. What about the 04?
So the system here uses a kind of binary logic. Evens are east, odds are west.
Wait, hold on. That's the golden rule right there.
That is the golden rule. Even numbers mean the east side of the park, the 5th Avenue side. Odd numbers mean the west side Central Park west.
Even is east. They both start with E. That's perfect.
It's the perfect mnemonic device. You can't forget it. So in our example, 04 is an even number.
So I'm on the eastern half of the park.
Exactly. If you saw 74 is 03, you'd be at 74th Street, but on the west side.
Okay, but then there's the depth part.
Okay.
Because the park is wide. East side is still pretty vague.
Right. Are you on the sidewalk or a quarter-mile inland?
And the numbers tell you that too.
They do. The magnitude of the number, how high or low it is, indicates your distance from the edge. The numbers start low at the edge and count up as you move toward the middle.
So it's a gradient.
Exactly. A low number like 04 means you're close to the street. You're almost right on top of Fifth Avenue.
Whereas if I saw, 7444.
Okay, so 44 is even, so you're still on the east side. But 44 is a high number. That means you are deep into the park, much closer to the center line.
So let's say it starts pouring rain and I need a taxi. I just need to find a path that makes the numbers go down.
That is exactly right. If the last 2 digits are descending, you're heading towards civilization. If they're going up, you're heading deeper into the woods.
It's like playing hot or cold with cast iron. I love it.
And it works without any other tools. You don't need to see the sun. You don't need a compass. You just need to know if the number is getting bigger or smaller.
So the next time you're in Central Park, New York, look out for those lampposts. Okay, a few dates for this coming month, February. The 6th of February, the Winter Olympics begin. And there are links to each of these events in the newsletter. So, well, not the events themselves, but the mathematics that you could use as an excuse because the event is taking place. So, 6th of February, Winter Olympics. The 6th of February also has a palindromic date. And there's lots of maths around palindromes, so that might be a good thing to mention. On the 14th of February is Valentine's Day. And I'm sure you probably know from previous years there's a Valentine starter for that day. On the 17th of February it's Pancake Day, and there's a pancake investigation on the site. And as I said before, the 17th of February is Chinese New Year. So, finally, the answer to last month's puzzle, which was...
My New Year's resolution is to paint the long fence that goes all the way around Tran Towers. In January, I will paint 1/12 of the fence. In February, I'll paint 2/12 of the length of fence remaining. In March, I'll paint 3/12 of the remaining portion of the fence, and so on throughout the year. When during the year will I require the most paint?
The answer is March and April. And if you want to see some methods of how that was arrived at, have a look at the online version of the newsletter, transom.org/newsletter, and scroll down to the comments section.
Then the puzzle's been solved. The mystery ends. There's nothing too hard for Transom's great friends.
Oh, there was an extension as well for rocket scientists. And they were asked, what if there were X months in a year instead of 12? Well, I'm certainly no rocket scientist, but a little bit of research tells me that it's going to be the nearest month to the square root of X is going to require the most paint. And that method does fall down slightly when identifying solutions where 2 months are require an equal amount of paint. Okay, don't forget this month's puzzle of the month. Let me know if you managed to solve it. But as far as this podcast, that's all for now. Oh, I should say that I'll do algebra, I'll do trigonometry, I'll even do statistics. But geometry and graphing are where I draw the line.
Thank you for downloading and listening to the Transom podcast. You can find the website at www.transom.org, where you're welcome to use all of the activities absolutely free, or jump in with both feet and become a Transom subscriber.